one solution at the back there is to turn all of them into paper aeroplanes and throw it at galaxy. Where has it gone now? Okay, so there's a whole body of literature, again from which we are going to borrow, which is in the form of what's known as state space models. Starting point is mainly in the control literature, but we can find many interesting uses for this as well. So you think about a system which is characterized by some measurements you can make and define its state. It is in some state. From that state, you can make transitions into other states and keep going. And this system produces observations that you can observe, you can measure. And from what you have measured, your job is to estimate the state of the system. Okay? So the kind of concepts we will have here are states, how states change. We'll call it dynamics. And observation from system. So knowledge of how the system changes and what you observe from the system, your job is to, from the observation, infer the state. From observation, estimate state. So that's a general problem setting. Because it comes from control, I can say something like, this could be states of some complex plant in which there are lots and lots of reactions taking place, and you can specify pressure, viscosity, whatever that's happening as states of the system. But you are sitting here and you have an instrument with which you can observe something about that. Yeah. You might have knowledge of how things change here. You might have knowledge of how whatever that changes there drives your instrument, what you measure from that. And based on what you measured, you want to know what's going on inside. Okay? So that's what we write. So we'll come back to this next week once again, and I'll tell you what this thing does. So how do states change? And I'll try and refer back to this autorecursive process on this. Yeah? So the way we would write how states change at time n, what was it at time n minus 1? What would it be at time n? It could be linear, it could be nonlinear, it could be anything. Let's write a very simple one. The simplest way the state can change is by a random walk. So the current state is just the same as the previous one, plus some disturbance. Yeah? I'm going to take a pause and remind the gentleman to pass it on quite fast. Can you quickly take yours and pass it on? If you can't find it, pass it on, and then we'll find yours later. Yeah? Because I would like you to reach the other end. That's my goal. One needs to have achievable goals. Okay, so let's assume a very simple random walk of the dynamics of a system. So this system internally is just moving randomly little by little. Yeah. It could be more complicated, but then the resulting estimation would be more complicated. It's much easier to start from a very simple one. Let's write some observations. My observation y at time n is my theta at time n transpose, some x of n as input, plus some noise. So I'm going to say this for the state is a vector, so there are 10 or 15 of them. My observation is scalar, because I'm writing a univariate time series that I'm trying to model. Yeah. So I'm observing something from some underlying state that's randomly moving by a linear function. And there's some noise in this. Okay? So we can say this one as process noise is the term used for this. This one we are going to say measurement noise. Okay? So whenever we define noise, it's conventional. It's the simplest model of noise is Gaussian noise. So we're going to say this process noise is Gaussian distributed. It has zero mean. It's not theta, it's zero. It has zero mean and the covariance matrix, we're going to call it Q. Measurement noise, also Gaussian distributed, zero mean. Let's say the variance is R. Okay? What I have written is known in the literature as a state space model. There is a state dynamics, there is an observation you can make from it. Okay? Classic, much more useful state space models might have this as a function of this. It could be a linear function if I multiply this by a matrix. It could be a nonlinear function if I have some nonlinear function there. Yeah? So it could be a function of this. It could also have some external input into the system, could be driven by some other input. But so you can make a general case. What I have here is the simplest that I can describe. Okay. So what's your problem? Observe y and infer theta. So that's the learning problem we have. You stuck somewhere? So once you have that problem, observe y infer theta, there is a very elegant solution to that, which we will not formally derive, but use in our course. Okay, so I think we will run out of time, so I won't give you the solution to this, but I'll ask the two people from the signal processing course, what's the solution to this call? I just deliberately brought it off before asking them. Sorry? Solution to what? Okay, solution to the problem. That's the problem. You have a state space model as written up there. Yeah, there's a state dynamics. There is something you observe from that. You are sitting with an instrument with which you have observed y, and somebody tells you what's the best estimate of the state. You make an observation, you want to know what the hidden stuff is. And that solution is?
RMS. It's a common filter.
It's a common filter, yes, yeah, correct. Yeah? And the way that works is to say, I'm going to have an estimate of my unknown state at time n minus 1 using all the data up to time n minus 1. So this is going to be estimate at time n minus 1. This n minus 1 says using all data up to time n minus 1. Okay, so that's just setting the notation. So at time n minus 1, I have an estimate of what the underlying state is going to be, and I have used all the data up to time n minus 1. Okay? So if that definition is understood, that notation is understood, if I go and write theta n given n minus 1, what would that be?
Value of
when given all the data until
Up to
n
the
minus
previous
1.
point in time. So this is a prediction. Agreed? Just under my notation, you will allow me to use the word prediction to refer to this, because I'm going to say what's theta at time n using all the past data. Okay? And if I went from here to theta n given n, the step that I have performed is something I would call a correction. Yeah? And in order to do this one, I need to know how theta n is derived from theta n minus 1. It's the dynamics of the state. I can use this knowledge of the system, how the thing is changing, in order to make a prediction. In order to correct that prediction, I need new data. Let's call it yn. There's a very, very elegant structure that will evolve out of this. So from time n minus 1, I go to time n in 2 steps. I make a prediction, then I correct. Yeah? Then to n plus 1 by making a prediction and then making a correction. So that's the structure of this solution. I don't carry just my states that I have estimated. Remember, there is noise in this business. When I wrote the system, I wrote some noise processes in there. I also want to carry how uncertain I am about my estimates. Okay? So let me write the matrix P. So I have P n minus 1 given n minus 1, P n given n minus 1, and P n given n. So this is the error covariance matrix. Which is going to be updated exactly the same way. Predict, correct, predict, correct. Okay? So what I have written out as a structure here is in the space of my unknowns. So this is my space of the theta. Space of unknowns. I have an estimate and an error on it. There is a matrix. The estimate is a vector. Okay? In that space, you can imagine I have something like a Gaussian distribution. At the center, or the mean of that, is my theta. And how uncertain am I about that theta is contained in that matrix P. Okay? So I have an estimate and how uncertain am I. As new data arrives, I will keep moving this little by little. Okay? As more and more data arrive, I will be more and more certain of my estimate, and you would expect this uncertainty to shrink. If I didn't have any data, you have to initialize it with something. I would think there is some huge uncertainty. As more and more data arrive, I can update these things by these prediction, correction, and so on. And you would expect it to become more and more certain. And that's the structure of the Kalman filter. I haven't written out the precise equations for how to go from here to here and here to here, or this P to this P and this P to this P, which we'll do next week. Okay? But if you just Google for Kalman filter, you will find all this. This information is available in 1,000 different places. But mostly, they will start from the most generic formulation. Yeah? And that should not confuse you. So if you look at that state space model, I have written the simplest. I have said the dynamics is just a random walk. I have said the output is linear. Yeah? People would generally, textbooks would write the most complex thing you can think of, a linear transformation from theta n minus 1 to theta n. They will write some external input, and the noise is scaled by some matrix, and they will derive the equations for it. But even if you look at it, you will be able to work out that for the simplest model, the equations pop out quite easily. Okay? Where will we learn and use this? Just in one more minute. Your next task would be to, given some stock index, run a model like this to calculate how well you can predict the next one from the previous one, and so on. And if you run a model, then you make a prediction about what it's going to be. The difference between the prediction and the truth is an error. So from this kind of some index data, you can remove the relationships that you can model out of this and get a residual signal. So this is data. By applying a model, we can get a residual. Okay. I'll ask you to implement a paper in which they have calculated this residual by applying a model, and then try to explain this from other macroeconomic variables. So you can imagine that you observe FTSE index or S&P 500, some index, it's going up and down like that. What can I model just by looking at the time series? Yeah. You find that, you filter that out. When you filter it, then the residual, can it be explained by something else? Yeah, so that I thought was quite an elegant paper, so I'll give it to you. You can read it, learn it, and implement it and confirm whether what those guys claim is true or not. Just the same way the current one you're doing, you're trying to verify whether some of Hutchinson's claims in that paper are true. I'll give you another paper that does this. Okay? And before that, we'll go through this common filtering in a little bit more detail. Okay, where are the marked sheets so far? Have they reached the end? Yep. Okay, so anything remaining, give it to me.